This short video introduces a practical application of Gauss's law. This is your first introduction to what is called a parallel plate capacitor. A parallel plate capacitor is perhaps the easiest way to store electric potential energy. Okay, now what I'm going to diagram out here on the board is a situation involving two oppositely charged infinite sheets. They have the same charge density, a positive sigma and a negative sigma. The two sheets are parallel to each other, and they're separated by some distance in space. Let me go ahead and draw out the sheets in the following way. So let's say that, for example, right here, there we go, like so. This sheet here is positively charged, and then parallel to it, but separated from it in space like so, is a sheet that is negatively charged, negative sigma, like so. The charge densities are the same. Okay, now recall that for a single sheet, the magnitude of the electric field for a single sheet, the magnitude of the electric field E from Gauss's law is sigma over 2 epsilon naught. What we want to do is we want to draw out the electric fields associated with these sheets and then calculate what the net electric field is in all regions of space. Okay, now first of all, for the positive sheet, its electric field lines look like this. Like so. So it's important to realize that what I've drawn here is just the electric field for the top positive sheet. And now using a different color, I'm going to draw the electric field for the green, or rather for the negative sheet. I'll do so here in green. Now recall that for a negative charge, the electric field lines are towards the charge. So once again, it's important to realize that what I've drawn here in green is the electric field associated with the negative sheet. It has the same magnitude to its electric field as the positive sheet does. And now let's just go ahead and add up the vectors. For example, notice for the regions outside of the space between the two sheets, that is here and here, the electric fields cancel each other out. However, in the region in between the two sheets, notice that the electric field vectors point in the same direction, so then therefore they add together. Okay, now what I suggest that you do is draw another diagram. In this case, what I'm going to do is erase the electric fields here and here because they cancel each other out. So there is no net electric field outside of the spacing here between the two sheets. Therefore, what we can do in this geometrical situation is confine an electric field to the space between the two sheets. Like so. And the net electric field for the spacing in between the two sheets is this value here multiplied by 2. So here, the net E field in magnitude is sigma over epsilon naught. You will soon enough commit this expression here to memory when talking about the net electric field here in between the two sheets. Okay, now in a practical sense, arranging a charge configuration such as this is called a parallel plate capacitor. We refer to the sheets as plates, and they are pieces of metal. They are conducting plates. When we describe the net electric field here in between the two plates, we are ignoring what happens out towards the edges, that is here and here. Out towards the edges, the electric field, of course, is not a constant, and it kind of bows outwards like so as it goes from the positive plate to the negative plate. We are ignoring, as we say, edge effects when describing this. Okay, now we'll go through capacitors in some detail at a later date when we eventually get to chapter 24, but for now I'm introducing the idea to you here just in the context of our Gauss's law calculation. Parallel plate capacitors such as this is perhaps the easiest way to store electrical potential energy. Let me show you an example of a capacitor. It's not a parallel plate capacitor, but it is still a capacitor nonetheless. Okay, the capacitor I'm going to show you is what's referred to as a Leyden jar. The two plates are as follows. I have right here this inner conducting cup. That's going to be one plate. And then I have right here this outer conducting cup. This is going to be the other plate. And then the two plates, like so, are separated from each other by this cup of plastic. This cup of plastic is an insulating material, much like there's this gap, if you will, here in between these two conducting plates for the actual parallel plate capacitor. And then, using my Van de Graaff generator, I'm going to go ahead and charge up the plates. Exactly how this is done in terms of voltage, we'll get to that at a later date. But I'm going to go ahead and charge up the plates, for example, like so. And then ultimately work is being done in order to create the electric field in between the two plates. So then therefore it stores electrical potential energy. I can then discharge the capacitor by connecting the two plates to each other by means of this conducting wand. Like so. Let me try it again. Like so. I can even do this, for example, by hand. Like so. So that's a nice introduction to a capacitor.